Everyone, welcome back to Tech Junior Tutorials. My name's Lee Warwick Jr. and we're talking about Advent of Code. Today is day, it's actually over because today's the 26th, but today we're going to be talking about day 21, or I'm sorry, 22, which is a real bear of a problem. So not spoiler it, but I was not able to get part 2 on my own. I definitely had to look up the code on Reddit and read a whole bunch of solutions, and I still don't fully understand it. But let's see where things went wrong for day 22. So jumping in here, this one is Slam Shuffle, which is seemingly a straightforward problem. They're talking about a deck of cards that is 10,007 cards long, or has 10,007 cards. And they give you a bunch of operations that you're supposed to do. So they say the deck of cards obviously is being treated kind of like as a list or an array. And the first operation they show is basically just reversing a list. So that wasn't a big deal. And then they show cutting a deck, so slicing a list or an array. And then the interesting one is this deal with increment n, which basically is a modulo operation where you're doing like 0 times the increment number, so n, so 0 times n mod whatever the length of the deck is. So 0 times n mod 10 is 0, 1 times 10 mod 10 is 1, or 3 if n is 3, so on and so forth. So like you can see this progression, and then it wraps around because of the modulus operation, or modulo. So this is the set of 10 cards you should get after doing that one. So not super difficult. That's basically it for the instructions. And then they give you some more test cases where you have to parse this input. And after doing all these operations, this is the result you should get. So not too terrible. The very end of this, they ask you, what is the position of card 2019? So all the cards are 0 through 10,006. So you can do like an easy index of and find this card at the end of all these. The puzzle input itself is just a long list of those operations. So not too terrible. I was able to crack that pretty quickly, even using a super naive solution. So 10,007 isn't a big enough number that it slows down the computer when you're doing like all these loops and stuff to rearrange the cards. So basically, I wrote some pretty decent code to do this. But so for deal into a stack, that's super easy. Just reverse in any modern language. Cut n cards. Python has like really nice slice syntax for that. So slice from n to the end and from the beginning to n and create a new list from that. Deal with increment n is the interesting one where so I did this like the super naive way. I basically looked exactly at what they were doing and so added, let's see. So I'm popping off the top of the list. So I like reverse it and then pop off the top. So that gives me like the first card, the second card, third card, so on. And then I just add either n, or I'm sorry, add mod deck length n, or count by n if it's 0. So I just do that until the copy of the deck that I made that's reversed is empty. And that is able to do it pretty easily. And then parsing the input, super simple, especially compared to other days where you're just like looking at the word and say like, okay, if the operation is deal into a new stack, do that one. If it starts with cut, do that one. Grab n, which is the last word. So if you split by a space, you can grab the last word pretty easily, especially with -1 in Python. And then you can say like if the first word is deal and the last word is not stack, so you're not doing this one. Or you could have just done an else here. That would give you the last one, which is deal with increment n. So those functions, a simple if else, and then parse the inputs and call .index, right? And that gives you the index of 2019. So we can do that. Runs in like a half second, not a big deal. But the problem comes in part 2. So for part 2, this one is like, frustrating. So for this one, they talk about Halley's Comet. So you may think, especially coming from day 16, that there's some kind of loop that would happen. And logically, because we're dealing with a deck of cards, even though this is a huge number, if you shuffle a deck of cards, there's a finite number of combinations of those cards or orders of those cards. I'm sure it is some magnitude way larger than the actual deck size. So they give you these giant numbers to work with. So instead of a 10,000 card deck, now you have I don't even know how it's like a quadrillion card deck or something like that. And then they say that you arbitrarily decide to shuffle the cards another quadrillion something times. And then he even torments us and says like, hey, this is going to Stack Overflow. So this could have been a very straightforward problem, or at least a solvable problem with just some minor or intermediate programming knowledge. But because they ask basically the inverse of the beginning or the part 1, so here they ask what is the position of card 2019. Now they want to know what number is on the card in position 2020. So now they want the value of the card at the position instead of finding the position of the card. So basically, to do this, you have to work backwards. So you have to take the shuffled deck and basically, so you're looking at position 2020, you want to unshuffle it so that you get whatever 2020 started as, and then you can do a lookup, or basically because the cards are the position they start in, if you run it backwards, you should get the starting position, which is the card. So that's not too terrible to think about, and it's not too difficult to reverse the deck and do like the inverse operations. That's attainable, but like the combination of that plus the times that you have to iterate through this and unshuffle is what makes this one like basically impossible, unless you are a math magician, as somebody on Reddit put it. So there's a lot of frustrated people on this one, myself included. I was able to, while thinking about this, get pretty dang close to part 2 solution on my own, just kind of tooling around with it. So this is my naive solution for part 1. I actually rewrote it in the process of working on part 2 and realized that there is some formula for the position, because we don't actually care about the value of the card. We only care about position, either starting or end. So part 1 can be rewritten, and it runs noticeably faster, but not much. But essentially, you can get or derive math formula for each of those operations from part 1 instead of actually manipulating a list. So without actually making a list and traversing it, you just do some quick math and pop out the solution. So dealing into a new stack, instead of doing a array reverse or a list reverse or something like that, you do deck size minus position minus 1, mod the deck size, and that will give you the reversed or the inverse position. Cut n cards, position minus n, mod deck size, and then deal with increment n. You multiply n times the position, mod the deck size, that will give you the new position. So running that, you can see like completes instantly. Not a big deal. So note the answer 6,978. For part 2, basically I reverse this shuffle. So I plug in 6978, and then at the end I get 2019, so I get what I started with. We can pump this up a little bit. But the equations that I got for the inverse, I was only able to get 2 of them. So part of the problem here is that this is modular math. or modular arithmetic, which I'm familiar with modulo as a programmer. Like I've used it here and there, and I know of its existence, and whenever I need it, I can reach for it. But as far as solving stuff with modular arithmetic, that is something that's way outside of my wheelhouse. So the easiest way to explain it is if you think about a clock, like if you move 13 hours ahead on a clock, you can't come back and be at hour 13. You can only be hour 1 through 12. So you're circling that clock, and you can only be in a certain amount of positions. It's the same thing with a deck of cards. Like if you shuffle the deck or loop through it, if you deal 53 cards or something, you're just going to end up with the starting card. So modular arithmetic, apparently, because I've been poring over Reddit reading about this, it can handle like addition and subtraction is not a big deal. Multiplication, not a big deal. But the inverse of the multiplication from part 1, so here this n times position, you can't do n divided by position or position divided by n or anything like that, because there's no such thing as division in modular arithmetic. What does that mean? I'm not really sure. But an inverse modulo formula, as I was Googling this and really digging deep for a solution, I found that you can do a POW or an exponent to like n to the exponent of the deck size minus 2. And then this third value I'm not 100% on. I don't know what the z in a POW operation actually does. I've never had to use it. But that times the position mod the deck size will inverse deal with increment n. So even looking that up and getting that was not enough because of, like I said, having to iterate through this like a quadrillion times. So that's pretty much as far as I got for part 2. Even if you run this with the quick math version, doing an iteration over a quadrillion times or doing arithmetic a quadrillion times takes like terabytes of memory, and it would take like literal months to run. So it's impossible to brute force this one, like a couple of other ones have been. But the solution for this, essentially, once you get past this point, so I looked up somebody else's code. I basically copy pasted it off of Reddit and ran it just to see if I could get anything, because it was not going to happen because I can't become a mathematician overnight. So what they've got is obviously a lot more terse than the code I'm working with. It's very hard to read. But in essence, what it's doing is there are these equations, right? They are basically linear equations. So maybe you're familiar with like y equals mx plus b. These are linear equations, and they can be added together. So basically what you're meant to do is to parse the inputs and do some kind of math over that, where you combine all of these equations together, and then you get coefficients to plug into a formula at the end. And that formula, I don't even know if this guy has it in a readable form, but it's basically, if you think of A as like the multiplier, and then B is the offset. So like A times the current position, so some value A times the current position, plus some offset, or minus, mod the length of the deck. That formula is the basest form of all of these shuffle operations. So if you do that, boil that down, and then figure out these A and B coefficients and parse that times, I guess, the amount of iterations, you will get the answer in the end. But I have no idea how to do that math. That is way beyond me. So what this gentleman does is he has a couple formulas for calculating the A and B coefficients as he goes through a shuffle operation, and then he does something to it. He writes this giant formula. I have no idea what that does. It is like some inverse mod-ish thing times some other inverse mod-ish thing. mod the deck size, and then this R is used a couple times. So this is like, who freaking knows how to do this? You know, even programmers were on Reddit. People with computer science backgrounds that have taken discrete math, have worked with linear algebra and stuff, got on and were like, I don't remember how to do this. And, or there are people in these classes now and they can't do it. So I don't know who this freaking puzzle is for. This is like advent of math, not advent of code. The code, as you can see, there's not really any coding to it. It's like parsing an input for, like, parsing words for their values. But the actual solution has almost nothing to do with coding. So at least yesterday's day 21, that one was a little frustrating, but solvable. It was a logic puzzle, which obviously logic has a lot to do with programming. This one has nothing to do with programming. This has everything to do with math. The only thing that's programming-ish about this is that they're telling you, like, hey, you can cause a Stack Overflow, and you're working with what are essentially like big int values or approaching big int values, especially when you start adding and multiplying them together. So it's possible to get another Stack Overflow on your variable if you're not like running mod on this enough times when you're doing these calculations. But otherwise, there's almost like part 2 almost has nothing to do with part 1. They give you this thing about Halley's Comet, which, if you're unfamiliar, is a comet that circles the Earth like every 70-ish years. So that is like throwing you a hint that maybe this thing would loop and there would be some kind of trick to it. There's no trick. It's literally crunch college level math to get it. So that is not helpful. If anything, that's a red herring. And yeah, that's all I got. So I cheated and used somebody's solution on Reddit. I have a working knowledge of the high level solution and how it should work. I kind of came to most of that on my own, but I have no idea. I couldn't even break this down into more readable code because I don't know what this equation is supposed to do or where it started. There's no comments to this, obviously. Kudos to this fellow on Reddit, Zetter Dave, that got this and was able to solve this thing. But yeah, I am at a loss for how to explain how to do this. Again, I'm a programmer and not a mathematician. Somebody said on there that it was, I guess, fair to use a math problem on advent of code. Certainly the fellow that creates these puzzles, he is a computer scientist, obviously, and I mean, it's up to him what kind of puzzles he wants to use. But I don't know, this one, it feels like wasn't really fair. I guess he decides what fair is. It's his thing, but I feel like this left almost everybody in the dust. The fellow that even jumped on Reddit was like the upvoted solution. He even said like he didn't feel like most people would be able to get this, and he solved it. So that's all I've got for this one. If you want to see the cheat code run just to prove it to you, oh, there we go. That pops out the solution, so it works. But I couldn't begin to tell you how it works. Like I said, I tried to write this in like a more readable format, and I couldn't even get it to produce the same number. So I don't know what I was doing wrong. His inputs are the exact same as my inputs, so I didn't even have to change that. But yeah, this one just completely, I got nothing. I've been reading about it all day, here and there, a couple hours this morning and a little bit after work, and I still don't have a firm grasp on it. I've been bugging some folks in the Coding Blocks chat. You can see that hat over there. Like one fellow in there has gotten it, and he said, yeah, he used modular arithmetic, which he obviously was familiar with. So that's all I got for this one. Moving on to day 23. It is another int code problem. It has to do with running 50 int code computers at the same time. So I'm hoping I can do that without multi-threading because I'm unfamiliar with that as well. and we'll see how that one goes. But yeah, let me know how you're doing with these in the comments. Like, subscribe, all that stuff, and good luck to you. And I will see you on day 23.